everybody, welcome back. This video will be talking about techniques of proofs beyond the last video where we're talking about indirect proofs and proofs by contradiction and so forth. They were kind of a nuts and bolts introduction. Now we're going to go a little bit deeper into different proof techniques. We want to talk about proofs by cases, existence proofs, counterexamples. These are not mutually exclusive with the last set. In other words, you can do a proof by cases using contradiction, and we will. Right? These are different kinds of proof techniques besides what we've seen in the last videos. So let's jump right in. Proof by cases. A lot of times the most natural way to prove something is to break it up into cases. For example, suppose you want to prove that P implies not just Q, but Q and R. Well, then you just break the proof down into two cases. P implies Q, and you do that one. Then you do P implies R. So simple enough. It's really a two-part proof. We're proving two different things, and we just do each piece separately. Now, here's an example where it may not seem like that's what we need to do, but when you look at the definition of what's going on, it really is. For all real numbers x is less than or equal to the absolute value of x. So notice I've called that a lemma. That's a name for a baby theorem. It's something we're trying to prove here, but it's not super important. In fact, it's really kind of obvious. If you think about this, well, if x is positive, then x is its absolute value. So x is equal to the absolute value of x. If x is negative, then then the absolute value is positive, which is going to be bigger than any negative number. If x is 0, we're fine. So you see how I just, in thinking through what this meant, naturally was led to some cases. And as you think about, why would I have to worry about when x was positive and why x was negative? It's because of the definition. So remember, I've emphasized over and over and over and over and over again how important it is to know all the definitions. You have to have them memorized, otherwise you have no hope of being able to write any proofs about anything. So what's the definition of an absolute value? The definition of the absolute value of x is that it's x if x is bigger than or equal to 0, and it's negative x if x is less than 0. Now this always looks really weird when people see this the first time. They go, wait a minute, absolute values make things positive. How could absolute value of x be negative x? Well, look at it really closely. Absolute value of x is negative x if x itself is less than 0. In other words, if x is a negative number, the absolute value ought to make it positive. How do you make something positive? Well, one way to say that I'm going to, quote, make it positive is I multiply it by a negative 1. So if x is less than 0, say x were negative 3, then how do I take its absolute value and turn it into plus 3? I take that negative 3 and write negative, parentheses, negative 3. So negative x will be a positive number if x was already negative. Okay, that's the definition of absolute value, and you notice that it breaks things down nicely into two cases. So what this lemma really says is that for all real numbers x is less than or equal to the absolute value of x, but the definition of absolute value of x has two pieces. So this says that x is less than or equal to x if x is bigger than or equal to 0, and x is less than or equal to negative x if x is less than 0. So this really is a P implies Q and R kind of proof. So how do we do this? Well, case 1. Let's suppose that x is bigger than or equal to 0. Right? That's the first possibility for the absolute value, and lo and behold, the absolute value of x is just x, according to our definition. So we get equals there, and we're done. Case number 2. Suppose that x were negative. Okay? In that case, then the absolute value of x would be minus x, because I need to take that negative x and turn it positive. So the absolute value of x would be negative x. Okay, how does that help me? Well, then x, which is a negative number, would be less than negative x, which is a positive number. Again, even though it has a minus sign in front of it, remember x itself was negative. That's a little tricky to keep in mind, but that's definitely okay because x itself was negative in this case. And of course, negative x was equal to the absolute value of x, so there's my proof. And you see how proofs with absolute values in them, naturally lends itself to breaking things down into cases. We'll have lots of examples as we go through this class where the easiest way to do this is to look at different cases, and prove P implies Q, then turn around and prove P implies R. So we do it in several different parts. That's called a proof by cases. But you have to be careful. This was proving P implies Q and R. This was proving an and, right? If you want to prove something with an or, like P implies Q or R, then that's a little different. This is definitely not the same as proving that P implies Q or P implies R. Now that works with an and, okay, that's what we just said, but it doesn't work with an R. And you think, why in the world should that be? Okay, this definitely needs an example. So suppose that we have this implication. X is a real number implies, and then this giant thing on the right hand side, that X is bigger than or equal to 0 or X is less than 0. So this is exactly in the form of a P implies Q or R. The P part is X is a real number. The Q part is X is bigger than or equal to 0. Then the R part is X is less than 0. And of course that's true, right? If you have a real number, then either it's bigger than or equal to 0 or it's less than 0, right? So that's easy enough. But that's not the same as writing it as X is a real number implies X is bigger than or equal to 0, or X is a real number implies X is less than 0, because that's false. And then you go, wait, what? Okay, let's dissect this. Look at the first implication. X is a real number implies X is bigger than or equal to 0. That's wrong because some numbers are negative. So that's definitely a false implication. What about the second one? X is a real number implies X is less than 0. Well, that's false too, right? Because there are definitely some positive numbers. In fact, that leaves out 0. So I have false or false. So of course, taken together, that's a false statement. Okay. Okay. Well, so how in the world do you prove something with that P implies Q or R? Well, there's a very awesome tautology that rides to the rescue here, and it's this: P implies parentheses Q or R is equivalent to P and not Q implies R. Now you can write out truth tables to check all this, but if you stop and think about it for a second, this makes perfectly good sense. So let me rephrase it slightly. So what we'd like to prove is that P implies that either Q has to be true or R is true, right? One or the other. Um, so that's the same as saying, okay, let's suppose that P is true, but Q isn't. Then the only alternative left is that R has to be true, right? Because if we're assuming P and we've ruled out the case of Q being true, then that has to imply that R is true. Now I've used Q and R here. You could switch those. You could assume that P is true and R isn't. That would have to imply that Q is true. Either one of those would be an equivalent um, implication. So we could use that to do our or statements. For example, if you looked at the example we had a second ago, that X is a real number implies that X is bigger than or equal to 0 or X is less than 0. That would be equivalent to this statement. X is a real number and not X is bigger than or equal to 0. That would have to imply X is less than 0. That's certainly true, because if X is a real number and it's not positive or 0, then it's got to be negative. Okay, so how could we use something like that? Right? Well, here's kind of an oddly worded statement, but lots of baby problems like this where we're just getting started sound oddly worded. So if you have a real number and the sum of that real number with itself equals its square, okay, that's weird. What does that really mean? So let's say our real number is x. That means that x plus itself, so x plus x, equals what you get when you square it. So what we're really talking about is the equation x plus x equals x squared. Okay? If that's true, then the number must be 0 or 2. So that's definitely a true fact, and we're going to prove it. Okay? So I'm going to do it using this trick I said a second ago about proving that a statement of the form P implies parentheses Q or R. Because in this case, our P would be the sum of a real number with itself equals its square. The Q would be that that number is 2, and the R would be that that number is 0. Right? So, in other words, if x plus x equals x squared, then we're trying to prove that x is equal to 2 or x is equal to 0. And we'll do that by assuming the p part, okay, and not the x equals 0 part. So let's suppose that x plus x is x squared and the x isn't 2. X isn't 0. Then I just have to prove x is 2. Okay? And that's easy enough because if I look at the equation x plus x equals x squared, of course that's the equation 2x equals x squared. Since we're assuming that x isn't 0, I can divide both sides by 0, or not by 0. Dividing by 0 is bad. Since we're assuming that x isn't 0, I can divide by x. Then that tells me that x has to be 2. Now I could have done it the other way around. I could have assumed that 2x equals x squared and that x wasn't 2. The arithmetic gets a little trickier, but the algebra works out the same way, and you can show that x is 0. Okay, that leads us to existence proofs. So we've talked about proofs by cases and having to break things down into different parts. But a lot of times what we were looking to prove is not something with different parts, but prove an existence statement. Like there exists x such that p of x. So not an implication necessarily, just there exists an x so that p of x is true. Okay? Well, there's two ways to do this sort of thing. They're what we call constructive proofs. That means we go actually find the x. Okay? In that last problem, we had an equation, we could try to solve it, that'd be finding a number, right? That's a constructive kind of proof. We actually find an x. A non-constructive proof is that we show the x exists, but we don't actually go and calculate what it is. For example, one easy way to do this is to assume that x doesn't exist and then get a contradiction. So a non-constructive existence proof is often done using a proof by contradiction. Wow, that was a mouthful. So if you go back and re-listen to that sentence and understand exactly what it said, then that means you really understood this lecture and the last one. Okay? So remember what we talked about in the last video about direct proofs, indirect proofs, proofs by contradiction. Those can show up in an existence proof or in a proof by cases. Those are not mutually exclusive things. And so, in fact, we'll do an example in just a second where we do a non-constructive proof using a proof by contradiction. Right? But let's do a constructive proof first. Right? So here's another really obvious, easy fact. There is a real root. In other words, a place where this polynomial is 0 for x squared plus 2x minus 3. Somewhere between 0 and 2. Okay? There's definitely a number between 0 and 2 that when you plug it into x squared plus 2x minus 3, you get 0. Okay? Well, here's my constructive proof. Super easy. Notice that when I plug in 1, 1 squared plus 2 times 1 minus 3 equals 0, you get 0 there, so 1's a root. So ding, 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 we're done. Now, that was not very helpful to the reader, right? I mean, I just magically pulled a 1 out of my hat and stuck it into the polynomial, and voila, it worked. Okay, so there was no indication here where the 1 came from or why we should use it. So maybe a better proof, at least that helps you understand what in the world's going on, is you could write out what you actually did to find the 1, which is you take your polynomial, x squared plus 2x minus 3, it factors into x minus 1 and x plus 3, which means your roots have to be 1 and negative 3. Or another way to say that is just notice when I plug in the 1, I get 1 minus 1 times 1 plus 3. So it's definitely going to give me a 0 for this polynomial when I plug in 1. So that's a constructive proof. We actually go find the thing I'm claiming exists. A non-constructive proof is, well, it sounds more complicated and it's kind of cleverer. It does lack the satisfaction of being able to, at the end, go, oh, there's the thing that I said exists. But some of the most important theorems in mathematics have non-constructive proofs. In other words, the the thing that they're claiming exists, they just prove that it exists. They don't give you a recipe for how to find it. So here's an example. Let's go back to our function, um, x squared plus 2x minus 3. Notice that's a continuous function. Now, we will talk a lot about continuous functions later, but I'm going to assume everybody remembers basic Cal 1 stuff where we know a continuous function. If nothing else, remember that you can draw the graph without picking up your pencil. There's a real definition for continuous, and we'll get to that later in the course. But if you just remember the basic idea from calculus about how this works, that's enough to understand how the proof goes. But also, I'm trying to show, remember that there's a root between 0 and 2. If I plug in 0, I get negative 3. If I plug in 2, I get 5. So what that means is my function switches signs between 0 and 2. Or if I were to try to graph this, I'd plot the point 0 and negative 3. So when I plug in 0, I plot that below the x-axis. When I plug in 2, I get 5, which means I plot that point above the x-axis. So somewhere in between, because I can't pick up my pencil when I draw the graph, I have to have crossed the axis somewhere between 0 and 2 on my way from y equals negative 3 up to y equals 5. Have to hit 0 in there somewhere. I don't know where. I haven't proved where it happens, but I have proved that it does have to cross the axis somewhere. There has to be a place, an x value, that I could plug in and get 0 somewhere. That's the essence of a non-constructive proof. I don't produce the x, I just prove to you there has to be one. Here's another non-constructive proof that is really a proof by contradiction. So let's suppose that this polynomial, x squared plus 2x minus 3, does not have a root between 0 and 2. Well, remember it was continuous, and when I plugged in 0, I got negative 3. If f is never negative, sorry, if f is never 0 on that interval, in other words, it never has a root between 0 and 2, which is what we're assuming, then it never crosses the axis and turns positive, so f has to be negative on the whole interval. But of course, when I plug in 2, I get 5, which is a contradiction because that's positive. So again, you can see here how proofs by contradiction, indirect proofs, direct proofs can all enter into the picture when you're doing an existence proof or a proof by cases or whatever. Okay, that was a existence kind of proof. What if you want to prove or disprove a universal statement? Especially if you want to disprove one, right? If you want to disprove for all x, p of x. Well, that's kind of cool because if you want to prove that for all x, p of x is false, right, all you have to do is prove its negation, which would be there exists an x such that not p of x. In other words, all you have to do is produce one x for which p of x is false. Right? And that x is called a counterexample. So to disprove a universal statement like for all x, if you again not proving it, disproving it, then you just have to produce a counterexample. Find me one x where p is false. Here's an example. Suppose you want to disprove the statement that every continuous function is differentiable. Now, the other direction is definitely true. Every differentiable function is continuous. But this direction is wrong. Continuous functions, every continuous function is differentiable. That's a false statement. And to prove that it's false, all I have to do is find one continuous function which is not differentiable. And we know one. In fact, we've already seen one in this video. Absolute value of x is a function. Because remember, absolute value of x, the graph looks like a V and has that point there at the origin where the V makes a corner. When you have a corner like that, you have a function which is not differentiable, even though it is continuous. So there's our counterexample. Not every continuous function is differentiable. The other direction we'll prove eventually. That'll be an important theorem for us. But this gives us an idea of how we can put together all the various proof techniques we've seen so far. Indirect proofs, direct proofs, and then use them to prove things in various parts using cases, or to prove an existence proof, or to prove that a universal statement is wrong by getting a counterexample. And that's what we've done here.